Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. Now let's get started on our set of questions for today's session. Okay, so question number 1. Asks, what are delocalized electrons? Okay, so delocalized electrons are electrons in a molecule or ion or solid metal that are not associated with a single atom or covalent bond. Okay, so realistically, when we have electrons that are in like an ion that is negatively charged, or when we have like double bonds in a structure, they don't really like stay put in that one location. They tend to move around. And that's where we get the term delocalized electrons. So for example, let's say we had different resonance structures. And we had this nitrate ion. Like that has this structure. And we have the two oxygens that are negatively charged. So these oxygens just don't keep like the negative charge permanently. They can move around even to the topmost oxygen, like so. So it can be on the topmost oxygen, and now this can have the double bond. This one still has a negative charge. And again, the third oxygen can have the double bond, and then these two can have the negative charge. Like so. And same with like a benzene. So benzene has double bonds on every other carbon, but it can also be drawn like this, where it's on these carbons. So that's why typically when we draw benzene and when we show that it is aromatic, it's easier to just put a circle in the middle, and this tells us that it is resonance stabilized. Okay, so now let's see what the junior tutor said. Sometimes, instead of binding between the atoms, electrons freely move around and delocalize themselves to three or more atoms. These are called delocalized electrons. Delocalized electrons form an electron cloud in which all electrons are distributed over a whole molecular atom. They are either pi electrons or electrons unshared from non-bonding electrons, so like lone pairs. Delocalized electrons are also predominant in metallic solids because electrons are freely distributed within the surface of the metal, which makes them a good conductor of electricity. As such, delocalized electrons can affect the physical property of a material depending on its type and composition. For example, diamond, despite being an allotrope of carbon, is a good conductor due to the delocalization of loosely bound electrons in its crystal structure. Okay, so this solution is correct. Okay, so question number 2. For the molecule CH2Cl2, so this is dichloromethane. Draw the Lewis structure, determine the geometry, and determine whether the compound is polar or nonpolar. So when drawing out the Lewis structure, we first need to calculate the total number of valence electrons. So carbon has 4 valence electrons, hydrogen has 1, and since we have 2 hydrogen atoms, we multiply this by 2, and chlorine has 7. And again, we would multiply this by 2 to give us a total of 20 valence electrons. So now when we draw out the Lewis structure, we can start off by drawing out a skeletal structure with carbon as our central atom. And then I can show the 2 bonds to hydrogen and 2 bonds to chlorine. And now I can fill out the octet in chlorine by drawing in all of the lone pairs. Okay, so if I count out all the electrons I have so far, where each bond contains 2 bonded atoms, you can see that I already have my 20 electrons drawn in the structure to have the correct Lewis structure. So now we need to determine the geometry of this structure, and to do that we can analyze the central carbon atom. So if we look at the carbon, it has 0 lone pairs, and it has 4 bonded atoms. So by using a Vesper theory table, like so, when we have 4 bonded atoms and 0 lone pairs, we have a tetrahedral molecular shape and electron geometry. Okay, so for the last part, we need to determine whether or not this compound is polar or nonpolar. So to do this, we need to determine whether or not we have any polar bonds in this molecule. So to determine the polarity of a bond, we need to look at the difference in electronegativity values of the atoms involved in the bonds. So for example, to determine the difference in electronegativity, between carbon and hydrogen, we need to look up the electronegativity values for both carbon and hydrogen, and then find the difference between the two. Okay, so here's one chart, or periodic table, that lists all of their electronegativity values. So it's kind of rounded off, but for carbon, its electronegativity value is 2.5, and hydrogen's is 2.1. So the difference between the two is 0.4. So this makes the carbon-hydrogen bond nonpolar. And we know that because their difference in electronegativity is less than or equal to, well, equal to in our case, 0.4. Okay, so now let's calculate the electronegativity difference between carbon and chlorine. So chlorine's electronegativity value is 3, and carbon's was 2.5. So the difference between these two is 0.5. The carbon-chlorine bond is polar. So this is because its electronegativity difference is greater than 0.4, but less than 1.69. So now that we know that the carbon-chlorine bond is polar, we can show dipole moments towards our chlorines in the molecule, like so. So we have an overall non-zero dipole moment since the hydrogens aren't electronegative enough to cancel out the dipole moments. So therefore, CH2Cl2 is a polar molecule, since we have an overall non-zero dipole moment. Okay, so let's see what the junior tutor said. Get the total number of valence electrons for the molecule, so they also got 20. Using this information, construct a Lewis structure in such a way that the octet of each atom is complete. Okay, so they showed a 3D structure. And looking at its structure, CH2Cl2 has a carbon as the central atom, 2 hydrogens, 2 chlorines, so it has a tetrahedral geometry. And because the 2 chlorine bonds create a dipole moment towards chlorine, since chlorine is more electronegative, this creates a net dipole moment. Thus, we have a polar molecule. Okay, so this solution is correct. Okay, so I'm just waiting for this. Okay. Okay, so now we are on to question number 3. Draw 2 Lewis structures for a compound with the formula C4H10. No atom bears a charge, and all carbon atoms have complete octets. So let's try to draw two different structures for C4H10. We could have all our carbons just in a line like this. And let's see what happens if we draw out just all of our hydrogens without forming any double bonds or triple bonds. And then we'll count out to see how many hydrogens there are. We have 8 plus 2, which is 10. So this is one of the structures that can have this formula, and it is called butane. So another thing that we could try out is if we had a 3-carbon chain, and then another carbon going down like so. And now we'll again fill in all of the hydrogens on the carbons so that they have 4 bonds in total. Like so. So this is also C4H10, and if we were to name it, we would number the carbons 1, 2, and 3. So on carbon 2, we have a methyl group. So therefore, this is called 2-methyl. And the 3-carbon chain tells us that it is propane. So 2-methyl propane. And notice that we can no longer move around the carbons in such a way that we have more configurations, because if we were to put a carbon group on or another methyl group on either carbon 1 or 3, then we would just end up getting butane again. So these are just the 2 Lewis structures that you could form with the formula C4H10. Okay, so the junior tutor said that the given compound can be represented as 2 different isomers, which are butane and 2-methylpropane. They calculated the number of valence electrons for both of them, and then they got 26, so they have butane and 2-methylpropane. Okay, so this solution is correct. Okay, so question number 4. We need to write multiple Lewis structures. Yeah, we do. For each of these molecules and each of these ions, also showing the resonance forms. So for A, we have ammonium hydroxide. So first, let's calculate the total number of valence electrons for this molecule. Nitrogen has 5. Hydrogen has 1. And we have 3 hydrogen atoms, so we multiply this by 3. And oxygen has 6, giving us a total of 14 valence electrons. Okay, so now let's draw out a Lewis structure. So our nitrogen can be bonded with the 2 hydrogens, and the oxygen can be bonded with the second hydrogen. So this is the skeletal structure of our compound, and if we were to count out all the electrons we have so far, where each bond contains 2 bonding electrons, we only have 8 out of the 14. So we need to draw out 6 more. So we can draw 2 lone pairs on oxygen and just another lone pair on our nitrogen to complete their octets. So now we have all our 14 electrons and the correct Lewis structure for ammonium hydroxide. Okay, so now let's look at our second compound, C2H3Cl. And let's calculate the total number of valence electrons. So carbon has 4, multiplied by 2. Hydrogen has 1, multiplied by 3. And chlorine just has the 7. So adding these up, we get a total of 18 valence electrons. So now let's draw out its skeletal structure with carbon that can be attached with the 3 hydrogens, and then another carbon is attached to the chlorine. So now let's draw out the lone pairs on our chlorine, and you can see that this is not a likely structure because our carbon doesn't have a full octet yet. So, and we also have only 16 electrons in this structure as well. So let's see what happens if we were to take one of the hydrogens from our first carbon and place it on our second carbon. You can see that both of them don't have a full octet yet until we form a double bond between the two. So now let's count out the electrons. And we have our 18 electrons, and everything has a full octet, with the exception of hydrogen, which has a duet, but that's okay. And we have the correct Lewis structure. Okay, so for compound letter C, we have carbon tetrachloride. So carbon has 4 valence electrons. Chlorine has 7 times 4. And we have a total of 32 electrons. Oh wait, I skipped one. Well, let's do this one first. So this is D. And we have 32 electrons. We will just have carbon. And we'll see what happens if we just have the 4 single bonds to chlorine and fill out all of the lone pairs. So now we have our full 32 electrons already drawn in the structure, so we know we have the correct Lewis structure. Let me just try to separate all of these, and I'll fit part C here. Which was HOCl. Hydrogen has 1 valence electron, oxygen has 6, and chlorine has 7, giving us a total of 14 valence electrons. So I think the simplest structure is just our oxygen in the middle, bonded with both hydrogen and chlorine. And if we counted out the electrons we've drawn so far in this structure, we only have 10 out of the 14, so the remaining 2 electrons will just go on our oxygen. Okay, so I know everything's out of order, but I think I can try to just fit E in this little section right here. Just so that we can fit all the parts in part 1. Okay, so this is E. We have C2, Br2. Calculating the total number of valence electrons. Carbon has 4 times 2. And bromine has 7 times 2. Giving us 22 valence electrons. So now, let's draw our 2 carbons bonded together, and each of them bonded to a bromine. Okay, so we now have this structure, and notice that our carbons don't have a full octet yet. Even if we drew a double bond, they still don't have a full octet. So now let's draw a triple bond. So they have a full octet now, and if we count out all the electrons, we have our 22 valence electrons accounted for. Okay, so these are the 5 Lewis structures for part A of question 4. And then we can draw the remaining on this page. So these are all ions now. And now we start off with the nitrite ion, NO2 minus. Let's make room for myself this time. So nitrogen has 5 valence electrons, and oxygen has 6, and we have 2 oxygens, so we multiply that by 2. And we also need to add an additional electron since this ion has an overall negative charge. So this gives us a total of 18 valence electrons. So now, if we drew out its skeletal structure, we have nitrogen single bonded to both of our oxygens. And if we were to fill in all of the lone pairs, then we have 16 out of the 18. But notice that our nitrogen doesn't have a full octet yet, so one of these oxygens needs to be double bonded. So now we have our 18 electrons, and we can show that this single bonded oxygen has a negative charge, and we can include its resonance structure just down here, where the first oxygen can have the negative charge, and the second oxygen will be double bonded. Okay, so these are the 2 Lewis structures, or resonance structures, that can be formed for part A. Now for part B, we have carbon dioxide. So carbon has 4 valence electrons, oxygen has 6, and we have 2 of them, giving us a total of 16 valence electrons. So now let's draw carbon as our central atom, and 2 single bonds to the oxygen. So notice that carbon doesn't have a full octet yet, so we can just make both of these double bonds and then fill in all of the lone pairs. So now we have our 18 electrons, our 16 electrons all accounted for, and the correct Lewis structure for carbon dioxide. And no more resonance structures can be formed since we have 2 double bonds on just both of the oxygens. So now we have SO3. So sulfur has 6 valence electrons. Oxygen also has 6, and we have 3 oxygen atoms, so we multiply that by 3 to give us a total of 24 valence electrons. So now, if we draw sulfur as our central atom and showed all of the bonds to the oxygens, and sulfur doesn't have a full octet yet. But actually, sulfur is one of those elements that are able to not follow the octet rule and have more than 8 electrons in its valence shell. So we can actually make all of these oxygens double bonded and then draw in all of the lone pairs that remain, like so. So this gives us our 24 electrons, and even if we calculated the formal charge of sulfur, we'll still get 0. So let's show how to do that. So formal charge is equal to the number of valence electrons minus the number of non-bonding electrons minus the number of bonding electrons divided by 2. So for sulfur, there are 6 valence electrons, 0 non-bonding electrons, and we have 6 bonds, so we have 12 bonding electrons in total divided by 2. You can see that it is still neutral. So this is the correct Lewis structure for SO3. And we don't have any more resonance structures because, again, all of the oxygens just have a double bond. And now let's do our last ion, which is CO3 2-, the carbonate ion. Carbon has 4, do it in the same format, 4 valence electrons. Oxygen has 6, and we have 3 oxygen atoms, so we multiply that by 3. And the overall 2- charge of the ion tells us we need to add an additional 2 electrons to the structure, giving us a total of 24 valence electrons. Okay, so now let's draw carbon as our central atom. And if we were to draw the 3 bonds to our oxygen groups, then you'll notice that carbon doesn't have a full octet, so we'll make one of them double bonded, and then just fill in all of the lone pairs. So if we count out all the electrons in this structure, we have 16, 19, 20, 22, 3. We have our 24 already accounted for. And these single bonded oxygens will carry negative charges, so that's where our 2- charge came from for this ion. So now we can actually draw resonance structures for this compound, just moving around the double bond. We could have this resonance structure. And this resonance structure. like so. Okay, so these are our 4 molecules for part B. Okay, so let's go back to part A to see what the junior tutor said. It's so much more disorganized compared to my second page. But anyways, this was ammonium hydroxide, so that's correct. And then the double bond with the chlorine and the hydrogen. Yep, so that's correct as well. C was like over here for some reason. Oh, they stopped at C. Well, the first 3 are correct. And they started off doing the 4th one. Okay, so the 3 solutions given are correct. The remaining structures are missing. Okay, so question number 5. Assign formal charges to each of the atoms in the nitrate ion NO3 minus. So first let's draw out the Lewis structure for the nitrate ion. We need to first calculate the total number of valence electrons for this ion. So nitrogen has 5, oxygen has 6, and we have 3 oxygen atoms, so we multiply this by 3. And since we have an overall negative charge, we need to add an additional electron. And if we were to add this all up, we get a total of 24 valence electrons. So now let's draw a skeletal structure where we have our nitrogen with a single bond to all of our oxygens. If we were to draw in all of the lone pairs, then our 24 electrons would be fulfilled. However, nitrogen doesn't have a full octet. So we need to make one of these have a double bond, like so. So now we have a Lewis structure for NO3. Oh, accidentally exited. Let me just go back to my page. Okay, anyways, we have our first Lewis structure, but we also need to assign the formal charges of each of these atoms. So the equation for formal charge is equal to the number of valence electrons minus the number of non-bonding electrons minus the number of bonding electrons divided by 2. Okay, so now let's calculate the formal charge of a single bonded oxygen. Oxygen has 6 valence electrons, and there are 6 non-bonding electrons, so in the form of the lone pairs, And there's just a single bond that contains 2 bonding electrons. So we divide that by 2 and get a formal charge equal to -1. So we can draw these 2 oxygens having a -1 formal charge. So now let's calculate the formal charge of the oxygen that is double bonded. Again, there are 6 valence electrons. This time there are 4 non-bonding electrons, and there are 2 bonds to the oxygen, so we have 4 bonding electrons divided by 2. So 6 minus 4 minus 2 is 0. So our double bonded oxygen is just neutral. And lastly, let's calculate the formal charge on nitrogen. Nitrogen has 5 valence electrons. There are 0 non-bonding electrons, so there are no lone pairs. And also the nitrogen has 4 bonds to it. So we have 8 bonding electrons divided by 2. So 5 minus 0 minus 4 is +1. So this makes our nitrogen positively charged. So if we were to calculate the overall charge of the ion, we can double check overall charge. We have -1, -1 plus 1, which makes it an overall -1 charge. And we can also show the resonance structures of this ion as well. So our first oxygen can have the double bond. Or the last oxygen can have the double bond as well. Okay, so these are the 3 resonance structures of the nitrate ion. And the junior tutor said that they calculated the total number of valence electrons. So they have 5 plus 18 plus 1 to get 24. The Lewis structure of nitrate ion is given as -1. Okay, so it's down here. And they also included the equation for formal charge, which is equal to the number of valence electrons minus the number of non-bonding electrons minus the number of bonding electrons divided by 2. So they calculated it. I feel like the images might be a little misplaced, but they have the example showing the formal charge of the double bonded oxygen, which should be 0. Nitrogens was +1, and oxygens were, the single bonded oxygens were -1. So this solution is correct. Okay, so question number 6. Predict the geometry of sulfur dichloride and the hybridization of sulfur atom. So let's calculate the total number of valence electrons. That way we can draw out a Lewis structure and then answer the question. So for sulfur, there are 6 valence electrons, and chlorine has 7. So we need to multiply 7 by 2. Since we have 2 chlorine atoms, in this molecule. So this gives us a total number of 20 valence electrons. So now let's draw our sulfur with 2 single bonds to our chlorines, and then fill in the remaining lone pairs on our chlorines as well. And you'll see that we have an overall electron count of 16 if each bond contains 2 bonding electrons. So we only have 16 out of the 20, so for the remaining 4, I can place them as lone pairs on my sulfur atom. So now we can predict the geometry and the hybridization by counting out the number of charge clouds our sulfur has. So sulfur has 2 lone pairs and 2 bonded atoms. So if we pull up a VSEPR theory chart, when we have 2 lone pairs and 2 bonded atoms, our molecular shape is bent. And our electron geometry is tetrahedral. And we also need to know the hybridization of the sulfur atom. So it is sp3 hybridized. And we also know that because there are 4 charge clouds on our sulfur. So charge clouds can refer to, or they can be lone pairs or bonded atoms. So we have 2 plus 2, which is equal to 4. So I can sum up all the different hybridizations if we were to count number of charge clouds. So for example, an atom is sp hybridized when there are 2 charge clouds. sp2 when there are 3 charge clouds. sp3, like our example, was the 4 charge clouds. And then once we get to more charge clouds, so let me pull up the second page of our VSEPR table. We have sp3d hybridization when we have 5. And we have sp3d2 when we have 6. So this is another simpler way of finding out the hybridization for a certain atom. And let's see what the junior tutor said. So to determine the total number of valence electrons, they got 20. Using this information, we can construct a Lewis structure, which is not shown, but they described it having 4 electron groups. So there's electron pair geometry and a bent molecular geometry. And since there are 4 electron groups, so these are what they call the charge clouds, this means that the hybridization is sp3. Okay, so the solution is correct. Okay, so question number 7. The molecular formula of acetyl salicylic acid, also known as aspirin, is one of the most commonly used pain relievers. C9H8O4. Part A is to calculate the molar mass of aspirin. So when calculating the molar mass, we need to know all the different molar masses of the atoms involved in aspirin. So these values can be found on your periodic table. We also need to take into account how many of each atom there is in the compound. So for example, for aspirin, we have 9 carbon atoms, so we take 9 times the molar mass of carbon plus 8 times the molar mass of hydrogen plus 4 times the molar mass of oxygen. So looking at a periodic table, you can find that the molar mass of carbon is 12.01 grams per mole. Hydrogen's is 1.01 grams per mole. And oxygen's is around 16 grams per mole. So adding all these values up, we get a total molar mass of 180.17 grams per mole. Okay, so this was part A. And for B, a typical aspirin tablet contains 500 milligrams of aspirin, or acetylsalicylic acid. What amount of moles are what amount in moles of molecules? I guess they mean how many moles are there and how many number of molecules are in a 500 milligram tablet. Okay, so we know that the mass is 500 milligrams. And we can convert this to grams since our molar mass is in grams per mole. So to convert milligrams to grams, we need to multiply by the conversion factor, where there are 1,000 milligrams in 1 gram. This is the same thing as dividing by 1,000. So we get 0.5 grams. Okay, so first we need to calculate the number of moles. And we can do that using the equation where number of moles is equal to mass over molar mass. So our mass was 0.5 grams, and our molar mass is what we found in the previous step, 180.17 grams per mole. So if we divide the two, we get 2.78 times 10 to the negative 3 moles. So now for step 2, we can find the number of molecules using Avogadro's number. Okay, so we know our number of moles was 2.78 times 10 to the negative 3. And if we multiply by Avogadro's number, this can tell us the number of molecules in this amount of moles. So Avogadro's number is 6.022 times 10 to the power of 23, and its units are in molecules per mole. So if we multiplied the two, you'll see that our units of moles will cancel out, and we're left with our value in molecules, which is 1.67 times 10 to the 21 molecules. So we have 2.78 times 10 to the 3 moles and 0.5 grams. And in molecules, it's 1.67 times 10 to the 21. Okay, so the junior tutor first calculated the molar mass of aspirin, and they also got 180 grams per mole. And in 500 milligram tablet of aspirin, there are 1.67 times 10 to the 21 molecules of aspirin. Okay, so this solution is correct. Okay, so those are all the questions for this session. If you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. And if you'd like to submit a question of your own, then check out the links in the description. Also, if you enjoyed today's video, you can give it a thumbs up and a comment, or you can share with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.